Hi there, folks. Today we're looking at some of the special cases for factoring. And once again, these are shortcuts that we're discussing here today. You can still do the first way we learned to factor trinomials, but there might be a little bit, especially in this first one, there's something you have to consider because as you're starting to look at these first couple, you're probably looking at it going, those are not trinomials, Mr. Jansen. Trinomials have 3 terms. Those are binomials because they each only have 2 terms, all right? So if you want to go old school, if you want to factor it without the shortcut we're going to learn, you have to think about those as trinomials, all right? So today's shortcuts, the first one I think is worthwhile. The second one, not so much, all right? When we get to that second shortcut, follow along, do what you can with it, and then if you immediately forget it after the lesson's done, that's okay. I'll forgive you. It's not going to hurt you in the long run, all right? So that's my gift to you today, all right? But if I look at this, the first thing it says here is we want to consider these first couple as trinomials, all right? Remember, a trinomial is of the form ax squared plus bx plus c. And when you look at these are not trinomials. They're binomials. They only have 2 terms. But the reason I wrote the ax squared plus bx plus c is I want us to think about which term is missing. Like, what is missing here that makes this not be a trinomial? All right, and hopefully you're looking at it going, well, it's got the x squared, and it's got the number at the end, but it's missing the thing with just x. It's missing the thing in the middle. So if I want to think of this as a trinomial, I basically just fill in the middle. I say, you know what? There's nothing in the middle here. Well, the math way of writing nothing is 0. So I'm going to put a plus 0x in the middle. That's the same thing as not having it there. That's what a 0 is. All right, but now it's written as a trinomial. So now I can do what I always do and build a bridge. So there's a 1 out front, and I build a bridge. That gives me a -4. 2 numbers that multiply to a -4, but add to a 0 is going to be a +2 and a -2. And because this one starts with a 1, I can use the other shortcut that I know and say, hey, you know what? I can go right to the 2 factors. This +2 becomes an x plus 2. And the -2 tells me to write an x minus 2. And I can only use that shortcut because this guy starts with a 1. All right? So that's my answer for this one, and that's it. I'm factoring it as a trinomial. And we haven't even used the shortcut for these particular types of problems yet. All right? We used a different shortcut that we learned. And honestly, you don't even need that. You could split that 0 up into a plus 2x and a minus 2x, and you could factor by grouping, and you'll get the same thing. Okay? If I look at the next one, again, the guy in the middle is missing. So I'm going to put a 0x in the middle. And now let's build a bridge. Now it's a trinomial. I build a bridge. And again, there's a 1 out front. 1 times -9 is a -9. 2 numbers that multiply to a -9 but add to a 0 are a +3 and a -3. Once again, I can use that other shortcut that I know. The a value is 1, so I can go right to the factors. Since the 2 values I came up with were a +3 and a -3, I'm going to do x plus 3 and an x minus 3. Okay? If I look at the next one, once again, yes, the middle term is missing, so I'm going to plug it in as a 0. 9x squared plus 0x minus 4. And now I can build a bridge. 9 times a -4 is a -36. 2 numbers that multiply to a -36 but add to a 0 are going to be a +6 and a -6. I can't use that other shortcut I know this time because that other shortcut only works when the a value is a 1. And this time the a value is a 9, all right? Because there's a 9, I have to split up the middle term and factor by grouping. And some of you have probably been doing that this way the whole time. Some of you aren't using that other shortcut, so this is going to be right up your alley. 9x squared, and then instead of 0x, it's 6x minus 6x. That's the same thing as 0, but now I have 4 terms, so now I can do my factor by grouping. Ready? Out of the first group, I'm going to factor out a 3, and it looks like they have an x in common. When I factor that out, it gives me a 3x plus 2. Out of the second group, those have a 2 in common, but I'm going to make it a -2 because that set of parentheses starts with a minus. And just be careful with your signs. When you factor it out, that's going to now be a +3x and a +2. So now I can see in parentheses I have the 3x plus 2. If I undo the distributive property, The other factor is a 3x and a minus 2. Done and done, okay? You can always factor these things by putting a 0 in the middle and then doing factoring the way we've always done it. You don't have to do the shortcut we're about to discuss. However, this shortcut I think is worth trying, okay? So this thing, these problems are called differences of squares, okay? A difference of squares, if you can see it down here. Let me scroll down just a little bit. There we go. I still want to be able to see the examples. So a difference of squares when we're subtracting two perfect squares. So if you remember your perfect square numbers, we talked about those a little bit earlier, but like 4 is a perfect square, 9 is a perfect square, 16 is a perfect square, 25 is a perfect square, 36 is a perfect square. So if you have two values being subtracted and everything there is a perfect square, you can immediately factor this into what we call conjugates. And conjugates are basically the same two binomials, but with different signs in between. Here's an example of conjugates right here. X plus 2 and x minus 2. It's the same binomial, but each one has a different sign. One's a plus, one's a minus. Here, this one, x plus 3, x minus 3. Those are conjugates because it's the same binomial, but one has a plus and one has a minus. Here, 3x minus 2 and 3x plus 2. Those are conjugates because it's the same binomial, but one's a plus and one's a minus, all right? And so if I recognize it's perfect squares being subtracted, I can immediately go right to the factors, and really coming up with those factors is really just a matter of taking the square root. Like here, you see this guy? It's a 4. The square root of 4 is a 2. See this guy? The square root of 9 is a 3. Over here, the square root of 9 is a 3. That's where I get the 3's from. The square root of 4 is a 2. That's where I get the 2's from. Okay? So we can use this shortcut to factor if we recognize the difference of squares. Okay? For example, if I look at this guy. X squared minus 49. And here's the thing. X squared is a perfect square. It's literally in the title. X squared is a perfect square. All right? So really, we just have to worry about the numbers as long as we have an x squared in there, okay? Look for perfect squares, make sure it's subtraction, all right? Difference of squares, subtraction of perfect squares. So here, x squared minus 49. 49 is a perfect square. X squared is a perfect square. We have subtraction, so this is a difference of squares. I can go right to the two binomials. When I do the square root, it's x times x will give me the x squared. So ask yourself, what's the square root of 49? What times itself will give me the 49? The answer is a 7. And now, conjugates, just one's a plus, one's a minus. Done and done. And again, if you forget this, put a 0 in the middle. Build a bridge. You'll get the same answer. All right? If you look at this guy, again, x squared is a perfect square, 100 is a perfect square. We have subtraction. This is a difference of squares. So it's going to factor into conjugates. Ready? Square root of x squared is an x. The square root of 100, what times itself gives me 100? It's a 10. One's a plus, one's a minus. That's how we factor a difference of squares. This is the shortcut, okay? X squared minus 81, those are perfect squares, and they're being subtracted. So it factors into conjugates. X times x. 81, the square root of that is a 9, so it's 9 times 9. One's a plus, one's a minus. It factors into conjugates. This is our shortcut. If I look at the next one, 4 is a perfect square. 121 is a perfect square. It's subtraction. So it's a difference of squares because I'm subtracting perfect squares. So it's going to factor into conjugates. And this one's a little bit trickier because I have more numbers essentially to take the square root of. Ready? The square root of 4 is a 2. So it's a 2x and a 2x. The square root of 121 is an 11. So it's an 11 and 11. And see, I know it's the square root because each of those things has to be the same. It has to be 2x times 2x because they have to be the same, and it has to multiply to 4x squared. It has to be 11 and 11 because they have to be the same, and they have to multiply to 121. And now one's a plus, one's a minus. If I look at the next one, 2 is not a perfect square. And 72 is also not a perfect square. So this is not a difference of squares. However, like I said before, you can only use shortcuts when you factor out the greatest common factor first. This one has a greatest common factor, a GCF of 2. So if I take the 2 out, it leaves me with an x squared minus 36. The 2 just kind of hangs along on the outside, but now look at the parentheses. Those are perfect squares and they're being subtracted. That's a difference of squares. So it factors into conjugates. X times x. To get to 36, it's 6 times 6. One's a plus, one's a minus. Done and done. If I look at the next one, 3 is not a perfect square, 48 is not a perfect square, but these have a greatest common factor of 3. If I factor the 3 out, that's an x squared minus 16. And now from here, x squared minus 16, those are perfect squares, so that's a difference of squares. The 3 stays on the outside. Difference of squares factors into conjugates. This has to be x times x. The 16 is 4 times 4. One's a plus, one's a minus. That's the shortcut for difference of squares. So most of the difficulty here comes in recognizing that those are perfect squares being subtracted. Okay. Once we recognize it, we go to the conjugates. Okay. One's a plus, one's a minus, same binomial twice. Okay. If I look at these guys, let's consider this. Now, this is the special case that it's probably not worth even memorizing. All right. It's nice for me to just show you this special case so you know it exists because it comes up in other areas of math, all right? If this is the last math course you ever take, well then, you know what? This shortcut's definitely not worth it, okay? And for the most part, most students don't memorize this as a shortcut. They just factor it the way they would always factor a trinomial, okay? So like this one, let's see what it looks like. I build a bridge. So there's a 1 out front. That's a 1 times 1 is a 1. Two numbers that multiply to a 1 but add to a negative 2 would be a negative 1 and a negative 1. See, multiply to a positive 1, add to a negative 2. I can use my other shortcut in this one because there's a 1 out front. So I can go right to x minus 1 times an x minus 1. And what's interesting now this time, see, last time I got the same binomial with different signs. This is literally the same binomial twice, which means I could leave it as this, or I could even write it as x minus 1 squared. So that's what squaring something means. It means I have that thing twice, all right? And here's the thing. If you're factoring this, I'll accept either one of these as an answer, okay? Different situations, we would use a different version of this thing. Sometimes we write the x minus 1 twice. Sometimes we write it as x minus 1 squared, okay? If I look at the next one, build a bridge. There's a 1 out front. Build a bridge, that's a 9. Two numbers that multiply to a 9 but add to a 6 are a positive 3 and a positive 3. So now I get to use my old shortcut on this. There's a 1 out front, so I can use that shortcut. So it's an x plus 3 and an x plus 3. And again, you could split up the middle term factor by grouping. You'll get this same thing. But now it's the same binomial. I could write it as x plus 3 squared is another way that you'll sometimes see this. And once again, I will accept either one of these as an answer. But it's special because it's the same, it's literally the same binomial twice. The last one was special because it was the same binomial with different signs. They were conjugates. This one's special because it's the same binomial twice. This guy, build a bridge. 4 times 1 is a 4. Two numbers that multiply to a 4 but add to a negative 4 are a negative 2 and a negative 2. I can't use my shortcut this time because it doesn't start with a 1, it starts with a 4. All right? So this one, I'm going to split up the middle term and factor by grouping. And once again, some of you might have been doing it this way the whole time anyway, and that's okay. So I rewrite the middle term, a minus 2 and a minus 2. I wrote a plus 2 for one of them. Let me fix it. That would have been disastrous, okay? So now I factor by grouping. Out of the first group, looks like I can factor out a 2 and an x, which leaves me with a 2x minus 1. Out of the second group, I have to factor something out. The only thing that I can factor out is a 1, and I'm going to make it a minus, a negative 1, because that set of parentheses starts with a minus. I always do that. And when I factor that out, that gives me a 2x and a minus 1. And so now in the parentheses, I have a 2x minus 1. And if I undo the distributive property, it's another 2x minus 1. Outside of those parentheses. So I could leave my answer like that, or I could actually write it like this, 2x minus 1 squared. And once again, I'll accept either one of these as the correct answer, but it's special because I got the same binomial twice. We call these perfect square trinomials. A trinomial that basically gives us something squared. It gives us the same thing twice. That's what something squared means, the same thing twice. All right? So a perfect square trinomial always factors into a binomial squared. Okay? The easiest way to identify a perfect square trinomial, some teacher will give you weird patterns where you look at A, B, and C. Remember, A, B, and C are the numbers that we have out front there. But looking at those patterns, oh my goodness, it's tough and it's weird to memorize, and you don't want to do that. The easiest way to recognize a perfect square trinomial is to build a bridge. If you build a bridge and the two numbers you get are the same, it's a perfect square trinomial. Here, if you build a bridge and get the same number twice, it's a perfect square trinomial. Here, you get the same number twice, it's a perfect square trinomial. All right? For example, if I look at this guy, all right, build a bridge. Let's see if it's a perfect square trinomial. I'd be shocked if it wasn't. But there's a 1 out front. I build a bridge. So that's a 25. Two numbers that multiply to a 25 but add to a -10 are a -5 and a -5. And see, I can tell it's a perfect square trinomial because I got the same two values here. So now with that said, if I want to go right to the squared version of this thing, I would just say, hey, in order to get this guy, I would have to take x and multiply it by itself. In order to get this guy, I would have to take 5 and multiply it by itself. And then the last piece of this shortcut is I steal the sign from my middle term. And now I can square it. And I'm done. That's it. Okay, so essentially it's the square root of the first guy, the square root of the last guy, steal the sign from the middle guy. And yeah, you're probably looking at that going, that doesn't really save me much work. Couldn't I use the shortcut with the 1? See, because there's a 1 out front, you could immediately go to x minus 5 times x minus 5, which then, of course, you could write as x minus 5 squared. So really, this shortcut so far has saved me a total of about 2 seconds worth of work, which doesn't really seem worth it now, does it? Sorry, I put a little squared there. Okay? If I look at the next one, same kind of thing. Easiest way to tell a perfect square trinomial is build a bridge. Two numbers that multiply to a 16 but add to an 8 are a 4 and a 4, a positive 4 and a positive 4. If I'm using that shortcut, ready? Here we go. What times itself gives me the x squared as an x? What times itself gives me the 16 as a 4? Steal the sign from that middle term, and it's squared. Done and done. All right? But once again, if you had used the shortcut because there's a 1 out front, you would have said, hey, I can go right to the two factors of x plus 4 and an x plus 4, which then you could rewrite as x plus 4 squared. It doesn't save me any work here, okay? If I look at this one, once again, build a bridge. That's a 9. Two numbers that multiply to a 9 but add to a -6 are a -3 and a -3. I can tell it's a perfect square trinomial because I got the same two numbers here, all right? So now this one, I don't have a 1 out front. This one could actually save me a little work. So right here, I say, hey, look at this 9x squared. The square root of 9 is a 3, so it's a 3x for this guy. I look at the last term and say, oh, what times itself gives me the 1 is a 1, and then I steal the sign from the middle coefficient. And now I slap the squared on there. Done and done. And that one, if you're looking at that going, that didn't make any sense to me. Well, then guess what? This shortcut is not worth your time, because the only time this shortcut saves you any work is in that last example. And if you don't get how it works in that last example, then you should not use this shortcut, okay? Instead, what's going to happen if you don't know the shortcut? You're going to go, well, I built a bridge. I don't have a 1 out front, so I'm going to rewrite that -6x as a -3x. Oh, that's a terrible looking 3. I can do better than that, I believe. And another -3x. I'm just going to split up the middle term and factor by grouping. Ready? Out of the first group, it looks like I can factor out a 3x, which leaves me with a 3x and a -1. Out of the second group, I have to factor something out, so I'm going to factor a 1, but I'm going to make it a -1 because that parenthesis started with a minus. That's going to leave me with a 3x minus 1. Oh, now look at that. In the parentheses, I have a 3x minus 1. And if I undo the distributive property, my other factor is also a 3x and a -1, which, of course, I could write as a 3x minus 1 squared. okay? And that took me all of 10 seconds. If you're really good at this, if you've really been practicing your factoring by grouping, this does not save you a lot of work, okay? So please understand that a perfect square trinomial, yeah, it's neat to understand that, okay, it factors in the same thing twice, all right? And maybe at some point you'll start looking for those kind of trinomials. That's why I show it to you now. The shortcut there is not really worth it unless you're doing a lot of these like me, okay? The one shortcut that we do have that's worth it, okay, is this guy right here, all right? The difference of squares. Perfect squares being subtracted is a difference of squares. It always factors into conjugates, so the same binomial, but one's a plus, one's a minus, okay?